All right, guys, we're back with a lecture on section 8.7. It's on an interesting technique for solving some differential equations, specifically called the variation of parameters method. This is an interesting method. It involves solving systems of equations as well as a small amount of integration. So we have a few required skills here. We need the ability to take determinants. And some basic integration techniques. Which integration techniques? Well, whatever comes up. But honestly, for most of the problems in this particular sort of aspect, you shouldn't expect anything too terribly complicated. Maybe some substitution, or maybe an integration by parts a little bit, but nothing too terrible. Okay. Okay. So I do have to cover one thing before I cover variation of parameters. Specifically, it's a process by which we take determinants called Cramer's rule. Okay, so Cramer's rule. Cramer's rule gives us an alternate method to solve systems of equations. Okay, I'm going to demonstrate Cramer's rule first, then I'll give you the actual definition so that we can see how this works. So let's get just a really simple system up here. I'll just make this one up off the top of my head. Let's say 2x1 plus 3x2 is equal to 1, and 4x1 minus x2 equals 5. Okay. And again, we could solve this in using 7th grade mathematics, right? You can use substitution, whatever you want, but specifically we're going to use Cramer's rule. And here's what Cramer's rule says. Cramer's rule says that x sub I is equal to the determinant of a sub I divided by the determinant of a. Now, of course, what the hell do these things mean? Well, A is exactly what we've been using. A is the representative matrix for this particular system. So in this particular case, A would be 2, 3, 4, -1. Okay. The determinant of which is fairly easy to compute here. The determinant of A would be, let's say, 2 times -1 is -2, minus 4 times 3, that's -2 minus 12, that's -14. Okay. So what the hell is A sub I then, right? Well, it's got to be related to A, and it turns out that A sub I is the matrix you get when you replace column I with the solution column, right? So A sub I is obtained from A by replacing column I with the solution column. Okay. Okay, so in this particular case, what would A sub 1 be? Okay, so A sub 1, that's I is 1, so I'm going to replace column 1, that's this column here, 2, 4, and I'm going to replace that column, okay, with my solution column, right? So column 2 won't change, but column 1, instead of being 2, 4, it's going to be 1, 5, right? 1, 5 is my solution column. So 1, 5. And there we go. We have A sub 1, right? A sub 2 I can make in the exact same way. A sub 2. Okay, again, here I is 2, so I want to keep column 1 the same. Column 1 is 2, 4. Again, obtaining this from A. But column 2, since it's A sub 2, gets replaced with the solution column. 1, 5. Okay. And now if I can go ahead and find the determinants of these. Again, these are 2 by 2 matrices. It's not terribly difficult. Okay. So determinant of A sub 1. I've got 1 times -1 is -1, minus 5 times 3, that's 15. That's -1 minus 15 is -16. And then again for A sub 2 here, okay, I've got 2 times 5 is 10, minus 4 times 1, that's 10 minus 4. That gives me 6. Okay? And here's what Cramer's rule says. Cramer's rule says that the solution to this particular system is x1 equals, so x1 equals determinant of A sub 1 divided by determinant of A. So in this particular case, negative 16 divided by negative 14, that's 8/7. And x sub 2 is the determinant of a sub 2, here at 6, divided by the determinant of a. So 6 over negative 14, or negative 3/7. There you go. There's the solution of my system. We can check those fairly easily. Let's see. Is 4 times x1 minus x2 equal to 5? 4 times x1 is, let's see, that would be 32/7 minus negative 3/7. That's 35/7, which is fine. There we go. Yeah, so this is Cramer's rule, okay? Now, why would I want this? Seems like more work than just doing some substitution or elimination of a variable. It is, but it does have one very clear advantage, and we're going to see that advantage whenever we do this variation of parameters problem. Okay, so what is variation of, again, keep this in mind, new skill. This is called Cramer's rule. Okay, again, just keep that in your mind now. We have a tool to solve systems of equations just involving taking some determinants. Okay, fine. I should point out, for Cramer's rule to work, of course, this can't be 0, right? I mean, you can't divide by 0. But if this were 0, the determinant of a is 0, wouldn't that mean that these weren't linearly independent? Yeah? And if these aren't linearly independent, then I know it's going to have infinitely many solutions, right? So Cramer's rule will find you unique solutions if you have a singular solution. It won't find you infinitely many solutions. As soon as you take the determinant of a, if it comes out to 0, you know there's infinitely many solutions. You'll have to do it another way. Okay, fine. Let's talk about variation of parameters. So what variation of parameters actually does, it gives you a way to find a particular solution. Remember back to the previous section we did, we talked about solutions for constant coefficient non-homogeneous linear differential equations, right? And what we discussed for non-homogeneous differential equations was that the solution for a non-homogeneous differential equation is just 2 parts. It's the solution for the homogeneous differential equation plus a particular solution, right? Well, variation of parameters gives us a method to find a particular solution, okay? So I'm going to do this in a second order example, just to make it, that's the smallest level at which this is an interesting problem. I should note that this can be extended to any order. I'll explain how to do that after I finish the example. So this is a very, very powerful technique. But let me work everything out just using 2 examples, to a second order first. So suppose you have the following differential equation. I've got y double prime plus a1 y prime plus a2 y. This is non-homogeneous equal to some function f here. Now before, we required these things a1 and a2 to be constant. I'm not going to require that now. These things can be functions as long as they're continuous on some interval, right? So I need a1 and a2 to be continuous on some interval I don't know what it is, whatever interval we're searching for a solution over, okay? And I'm not going to specify here, but I need a1 and a2 to be continuous on some, and for that matter, I need f to be continuous as well, okay? So let's say a1, a2, and f are continuous on some interval I. And furthermore, suppose that the associated complementary function, now remember, where do I get the complementary function from? The complementary function is the general solution to the homogeneous version, right, where that's 0, right? So suppose the complementary function is c1 y1 plus c2 y2, Okay, so there's my complementary function. Okay, let me put a side note in here. Okay, so we're going to put in a note here. So note y sub c is the general solution to y double prime plus a1 y prime plus y equals 0. Sorry, a2y equals 0, right? So again, that's the same function, but it's homogeneous instead of being non-homogeneous. Fine. Okay. So again, a lot of assumptions here, right? Then here's what I know. There exists a particular solution, okay? Then there exists y sub p, which is equal to u1 y1 plus u2 y2, where u1 and u2 satisfy the following system. y1 u1 prime plus y2 u2 prime equals 0, and y1 prime u1 prime plus y2 prime u2 prime is equal to f. Okay. Now I realize this seems like this definition got a little bit large and somewhat complex, but it's not. We're going to work through it here. It'll make more sense when we do an example. So variation of parameters. Yeah, fantastic, fantastic. And so let's talk about, so if I have a problem, let's sort of strategize here. If I have a problem that I'm going to solve using this particular method, what I'm going to do is I'm first going to solve for the complementary function, right? I'm first going to solve the homogeneous version, the complementary function. And then once I have the linearly independent basis vectors here for this solution space for the complementary function, I'm then going to put those into this system, and I'm going to solve for u1 prime and u2 prime. Okay? Okay, fine. Assuming I can solve a system, that will work. But now that I have u1 prime and u2 prime, well, of course, I can just integrate those to find u1 and u2, and then that gives me a particular solution. Okay? Then I know that the general solution here is just the complementary solution plus the particular solution. Okay, it's easier to sort of track everything that's happening if we do it by example. So let me go ahead and get a nice concrete example up here, and we'll see how this works. Okay. All right. Okay. All right, so let's say I have the following equation. I've got y double prime plus y equals secant x. Now, I know this is a constant coefficient. I know it's linear. The problem is I don't know what the annihilator for secant x is, right? So that's a problem, right? I don't know what the annihilator for secant x is, so I don't exactly know how to approach this using the method of annihilators and undetermined coefficients. I'm going to have to do this another way. Let's try it using variation of parameters method. Okay? So again, variation of parameters method, the first thing I want is the solution for the associated homogeneous differential equation, right? So here we go, associated homogeneous equation. First thing I want are the solutions to y double prime plus y equals 0. This is very, very easy. This is d squared plus 1 y equals 0. For the auxiliary equation, I get the roots plus or minus I, and we've done this probably several times now. I know that this corresponds to c1 cosine 1x, again that's 1i, plus c2 sine x. Okay, there's my complementary lines. There we go. Easy as pie, right? Now what I know then is that for the purposes of my variation of parameters method, y1 is cosine x and y2 is sine x. Okay, order is irrelevant. You can symmetric up to labeling, so that's not a huge deal. All right, so let's go ahead and solve for y sub p. I know y1 cosine x, y2, that's sine x. Okay. All right, now, the system that I want is, I'm going to write it down here because I'm going to have to erase it due to space, right? The system I want is y1 u1 prime plus y2 u2 prime equals 0, my second equation, y1 prime u1 prime plus y2 prime u2 prime equals, well, f. But in this particular case, f is secant x, right? That's my non-homogenous portion there. Okay, so you'll note that to fill this out, I actually need my derivatives. I need y1 prime and y2 prime. Let me go ahead and find those. So I got y1 prime is negative sine x, and y2 prime is cosine x. Okay, fantastic. All right, so knowing this, I can then fill in this particular system. Okay, so my system. My system is y1, so let's see, that's cosine x times u1 plus y2 sine x times u2, that equals 0. Second equation, y1 prime, so negative sine x times u1, oh, these are prime, crap, plus cosine x times u2 prime. That's equal to f. F here is secant x. Okay. Now we see the reason why Cramer's rule comes up. Man, elimination doesn't really work. I don't know what multiple of cosine x is going to give me positive sine x, so I can add and eliminate. I wouldn't even begin to know how to make row echelon form from these things. Well, I mean, I wouldn't want to. Okay. We have Cramer's rule. Cramer's rule is easy. Cramer's rule tells me that u sub 1 prime, this is my unknown parameter here, this is the determinant of a1 divided by the determinant of a. Seems pretty easy, right? So that's all I actually need. I actually just need the determinant of a, determinant of a1, and determinant of a2. So let's go ahead and do that. The determinant of a, that would be the determinant of cosine x, sine x, negative sine x, cosine x. And if we actually work this out, that's cosine squared minus negative sine squared, cosine squared plus sine squared, that's 1. That's fantastic, right? This is why you do problems out of the book. They come out nice. Okay. Let's talk about A1. Okay, so remember, A1, it's A, but you replace column 1 with the solution column. So A1 is, column 1 is 0 and secant x. Column 2 doesn't change, so it's sine x over cosine x. Okay? Determinant here, 0 times cosine is 0, minus secant times sine, that's negative tangent x. Sine times secant is tangent x. Okay? And lastly, I've got A2, determinant of A2. That's replacing the second column with my solution column. So my first column is the same, that's cosine x, negative sine x, 0, secant x, fantastic. Okay, let's get cosine times secant, well that's 1 actually, minus sine times 0, that's 0, 1 minus 0 is 1, fantastic. Okay, so what do I know? I can take all of these things now, and I can start putting them together. I know what u1 prime is. Okay, I know that u1 prime is the determinant of a1 divided by the determinant of a. It's negative tangent x over 1, or, well, negative tangent x. Okay. I know what u2 prime is. u2 prime is the determinant of a2, that's 1, divided by the determinant of a, also 1. So 1 over 1, well, that's 1. Okay? All right, fantastic. Well, again, I don't actually need u1 prime, u2. What I need is u1 and u2, but I can find those just by integrating these, right? The integral of u1 prime is u1. The integral of u2 prime is u2. Let's see what we get when we integrate here. I got to erase some of this stuff. Okay, well, I'm going to erase this part here. I'm just going to recopy u1 prime and u2 prime now that we found them. Okay, all right. All right, so let's see. So u1 prime is equal to negative tangent x, and u2 prime is equal to, well, 1. Okay, so I'm just going to integrate these in order to find u1 and u2. u1 here, u1 of x is going to be the integral of negative tangent x dx. We know what the integral of tangent is. The integral of tangent is the natural log or the absolute value of secant, or equivalently negative natural log of the absolute value of cosine, but two negatives would make it positive. So this is the natural log of the absolute value of cosine x. I'm going to come back to this in a second. u2 of x, that's the integral of 1 dx. The integral of 1 is just x. Now, I have a quick question. So, what I know, the part that you guys are probably screaming about in the watching the video now is that I'm missing some constants here, right? I'm using C1, I shouldn't be. So maybe C3 and C4, right? Gotta have some constants. The problem is, what I'm looking for are a U1 and a U2 which satisfy these conditions. I'll take any U1 and U2, and the conditions were that system, right? The conditions were that U1 and U2 satisfy y1 u1 prime plus y2 u2 prime equals 0 in the second equation, but all those use u1 and u2 prime, and it doesn't matter what these coefficients are, these functions will still satisfy that system. And what that means is that it doesn't matter what you choose for these coefficients, these particular choices are irrelevant. The u1 and the u2 you get from these coefficients, no matter what you choose, are still going to satisfy that system, which means they will still comprise a particular solution, right? Now, I've said this multiple times in class. This is one of those instances where I'm not looking for a specific thing that works. I'm looking for anything that works, right? And since I'm looking for anything that works, I'm going to make the nicest possible choice for these constants, which is, well, nothing, 0, right? Okay, so what does this tell me? This tells me now that I have u1 and u2, the variation of parameters theorem tells me that y sub p, so a particular solution, is u1 times y1, so natural log of the absolute value of cosine x times cosine x, plus u2 times y2, so plus x times sine x. Now, this gives me my general solution. Let me go and write that down. I'm going to bring up another point about this. Okay? So my general solution then, of course, is just my complementary function, the solution for the associated homogeneous differential equation, that's C1 cosine x plus C2 sine x, plus my particular function. Now, there's a tendency, because I know I thought this whenever I first started learning about differential equations in my undergraduate, there's a tendency to think that, well, if I know the homogeneous solution, well, I could just play around with this stuff enough to find a particular solution, right? If I'll take any particular solution, and any one will work, okay? Couldn't I just play around with it long enough to eventually find one? Yeah, man, but like how long would it take you to find something like this? Like how many things would you have tried before coming up with something like this to where you plug this in, if you take this and plug this in here, you're going to get secant x. That's really, really unlikely, right? Yeah. So a lot of the research in these differential, the field of differential equations, a lot of the research is trying to find more efficient ways to find particular solutions, and well, obviously also trying to find solution processes for things that are, well, not linear. So far, most of the things we've done is linear, but then again, this is your first differential equations course. Okay, so this is not bad. This is not a terrible process. It's easy to get lost. There are several steps. This is always the first one, finding that complementary function, and then you guys probably just practice a few times. Using Cramer's rule, and then solving for that U1 and U2, okay? Now, side note, it's minorly embarrassing, but every now and then I have students that can't integrate stuff like this, right? So please make sure that we're up on our basic integrations, yes? Okay. Now, this was second order, and I did mention that this could be applied to any order, and it can be extrapolated. I'm going to write that out, but I'm not going to get too deep into it. You can find the extension in your book on page, where are we? No, here we go. On page 552 and 553 in your book, they have that extension. Everything actually works the same. If you have again, a differential equation, we've got some nth order differential equation. So we've got a sub 1, n minus first derivative, et cetera, all the way down to a sub n minus 1 y prime plus a sub n y is equal to f. We assume that a sub I and f are continuous on an interval I for every index I. Basically, all of these a functions and f have to be continuous at the same time somewhere for this thing to have a solution. And I assume the same thing. I assume further. I still suppose that y sub c is c1 y1 plus c2 y2, et cetera, plus cn yn. I know I need n linearly independent solutions for the homogeneous version because this is nth order. And the key here is now the system of equations. Okay, the key here is the system. The system increases order by derivatives of y. So I need to solve for n things. I need an n by n system, and here's how we create it. Then y sub p equals u sub 1 y1 plus u sub 2 y2 plus blah, 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 plus u sub n yn, where, okay, here we go. So here's how I make my n by n system. The first equation is similar. It's y sub 1 u1 prime plus y sub 2 u2 prime, et cetera, plus y sub n un prime is equal to 0. Now, I need to make n minus 1 more equations. I need n equations, right? And the way I make the next equation is just to take a derivative of all the y's. Yeah? So my next equation will be y1 prime, u1 prime, y2 prime, u2 prime, etc., yn prime, un prime equals 0. And then the next one, y1 double prime, again, just take another derivative. So y1 double prime, u1 prime, y2 double prime, u2 prime. Notice that the u's don't change, the y's just get differentiated. And eventually, they all equal 0 until the very last one, right? So the very last equation, the very last version will equal f. And the question is, how many derivatives will I have to take? Well, I need n of these equations. The first one starts with 0 derivatives, and that's the first equation, which means the nth equation will have n minus 1 derivatives. So this will be y n minus first derivative u1 prime plus y2 n minus first derivative u2 prime plus yn n minus first derivative un prime, and that one equals f, right? So all of them equal 0 until the very last one equals f. Now, I said this could be extended to larger order, and it can, obviously. What's the problem we come up with? Man, this is not pleasant, right? Yeah, especially when you consider the fact that, again, when we're solving this system, when I told you about Cramer's rule, what I failed to mention and what we saw later on in the example was you're using Cramer's rule because the coefficients are not, no, they're not numerical coefficients, they're function coefficients, right? And so when you're solving this system for u1 through un prime, all those coefficients are sticking in those matrices for Cramer's rule and other things like that. Those are functions, not numbers. Okay, that makes computing these things much more difficult. Okay, all right. So that being said, obviously, students are always worried about tests for your exam. Don't worry about that crap, right? Because honestly, I only have a certain amount of time to get here. Like, I can't put a 5x5 on this thing and expect you to be able to solve it in under like 4 hours. So don't worry about that stuff. Make sure you practice. This is in, again, section 8.7 in your book. And again, I'll put up a few homework problems as well as maybe some interesting ones involving maybe some multi-stage mixing problems online. Okay? All right, guys.